Hey, good afternoon, AP Physics. It's been a weird couple of days where we've missed each other back and forth, and I feel like I just need to get us back on track a little bit and keep us moving forward. Particularly in a two-trimester AP class, we can't afford snow days like this, we can't afford to miss each other. So, give you some reminders here. We've been working with the biggest idea we have is that work is change in energy. Work's measured in joules, energy is measured in joules for a reason. To me, they're two sides of the same coin. It takes energy to do work. When you do work on something, you change its energy. We've got a slightly new looking formula for potential energy, gravitational potential energy, and that is that the change in gravitational potential energy, we're used to mgh, but what for us, y is height, same idea, we're good there. Here's our old formula for kinetic energy. The only thing, they don't write Ke, they write K. And we have been using the idea of conservation of energy, that if there's no frictional forces, that the gravitational energy and the kinetic energy keeps adding up to the same thing over and over and over. One thing we haven't seen just yet is the force that it takes to, let's say, pull back something like this, or maybe something more like this where it's got a spring in it. That we haven't seen yet. It should make sense to you, however, that the further you pull it back, if you ever play with these at all, the further you pull it back, the harder it is. That is, the further you pull it back, the more force there is. In fact, there's a direct relationship between the force that it takes to pull that spring back and the distance that you have pulled it back. And we're going to call the distance we pull it back x. What we're missing, however, is a constant in there. In fact, they actually call it the spring constant. The spring constant depends on how hard it is to pull it back. And you guys have played with these before. This is not hard to pull back at all, whereas this one's a lot more difficult. It has to do with the fact it's a stiffer spring, it's bigger around, it's just harder to pull back. And they call the spring constant K, not capital K, lowercase k, and that's a little bit confusing in the same chapter, but that's the way that it is. In fact, this is called Hooke's law. Hooke's law says, as an example, if you pull back the spring a little bit, and it takes a certain amount of force, and you pull it back 3 times as far, it takes exactly 3 times the force. That law works until you, let's say you could take this out until you pull it so far that you've mangled the spring. At that point, it doesn't work anymore. But again, K measures how hard it is to pull back the spring, how stiff the spring is. And there's units for it. And here's how they measure it. They take how far you've pulled it back, which in this case was 5 centimeters. And it took me 10 newtons of force to do that. That's when I top out the spring scale. What they do is they take the force that it took, which in our case was 10 newtons, and they divide by the distance in meters. And if you do that division, you're going to get, gosh, 2,000. If you do the division, yeah, that's going to be 20, so it's 200. So this spring scale has a constant of 200 newtons per meter. Now I could never pull this thing back a full meter, obviously, but it would take 200 newtons for every meter if I wanted to pull it back a full meter. And that's how all spring constants are measured. This one would obviously have a much bigger spring constant, because this one takes 50 newtons to pull it back. We can do the division, 50 newtons to pull it back the same 5 centimeters. I guess we're going to do it in meters. And if you do that division, you should get about 1,000. Okay? So spring constants are based on how hard it is to pull it back. The units are always newtons per meter. And again, it's an indication of how much force it takes to pull that spring back a full meter, even if you can't pull it back a full meter. So that's a new formula for us. K is slightly new for us. The other thing we haven't talked about before is when you do pull something back like this, or maybe something more like this, how much energy have you stored? Well, not surprisingly, it is dependent on how far you pull it back. The further you pull it back, the more energy you've stored. Not surprisingly, it's also dependent on K, because the further you pull, or the stronger the scale, and the stronger the spring you have, the more energy you have to do to put in to get it to pull back that far. What might be a little bit surprising, this variable is a little bit more important. It turns out to be a half in front of the whole thing, and when we have more time, I'll go through the explanation as to why that is. But that is the elastic energy stored in the spring, and this is close enough to a spring, so it'll still work for something like this. What we'd like to do is take an example and put all of the ideas we've used together to calculate this. Let's say I took one of these markers, pulled my crossbow back, put the marker in it, and shot the marker from a handheld height of this, which is probably about 1.2 meters. So all the information you need to know is that when I pulled this back, it was 17 centimeters from front to back. I started out with a force of 0, I measured it before I got on camera. At the end, it was 8 newtons of force. The mass of this marker happens to be 11 grams. I made up a coefficient of friction. As you shoot it, this has to slide along the barrel of the gun. I made up a coefficient of friction of about 0.1, which is pretty close. Again, I gave you a height of 1.2 meters. We could put all that stuff together and ask yourself, fine, once you shoot this, given all those ideas, how fast is that marker going when it hits the ground over here? And this is actually much like the lab that I'm going to ask you to do. But we could put a lot of things together. Here's two different ways to look at the same problem, and the answer is the same, not surprisingly. You could say, well, in the beginning, the marker Earth system has some gravitational potential energy, and because I have pulled it back in here, you could say that the marker crossbow system also has some spring stored energy. When it slides along the barrel of the gun, some work is going to be done by friction, we know that. By the time it gets down to the bottom, the only form of energy there is kinetic. And so you could approach this problem like that. You could look at it slightly differently and just look at the marker. Say, look, the marker is above the ground when it's here, so it's got some gravitational potential energy. You could look at it as when you pull this back and let it go, how the string pushes on the marker along the barrel of the gun. So you could look at it as the work done by the string instead. You're still going to lose some energy to friction, we know that. And at the end, there's only kinetic energy left. So you could answer this question, how fast is the marker going to be going when it hits the ground, two different ways, and they're definitely equivalent. We could find the potential energy stored in the spring by using an equation, 1/2 kx squared. Let's try that. I'll put a half in to start with. Okay. I would need to know k. Now remember, it's measured in newtons per meter, as in how much force did it take to pull it back a certain distance. Well, if I already know that it took 8 newtons to pull it back this distance, I would simply take the force divided by that distance. And that is k right there. We also said it's x squared, and so I could put my distance of 0.17 and square that. That's one way of finding the potential energy stored in the spring marker system. Alternatively, if I wanted to find the work done, instead of looking at it as what's energy stored, but how much work does the string do as it shoves the marker along the barrel of the gun, I would simply take our old formula for work, which is average force, and the average force, starting at 0 and ending at 8, is simply 4, and the distance this thing got shoved along the barrel of the gun was simply 17 centimeters. Now, strangely enough, these come out to be exactly the same number. In fact, you can even see it coming. Half of 8 is 4, and down here I have 2 0.17s on top and 1 on the bottom, and that simply leaves me with 0.17 on the top. So either way you want to do this, either one of these numbers comes out to 0.68, and we should probably put units in, which are joules. Now we can finish the rest of it. You could find the gravitational potential energy of the marker. I think we can probably see this in red. So M, the mass of the marker, in kilograms. G, our height, is 1.2. We just saw how either one of these numbers are exactly the same number. So I would simply add 0.68 into this. Maybe we'll change colors here. Somewhere along the way, we need to find the work done by friction. We know that the work done by friction is the frictional force times the distance traveled. And we also know that frictional forces are equal to the normal force, right? Normal force times the coefficient of friction, which happens to be 0.1. We also know that the normal force in this case is actually equal to the weight of the marker. So we can put all those numbers in, and I've done that. I'd like you to try to finish this whole thing. And again, at the end, when this thing hits the very, very end at the ground, the only thing left is kinetic energy. So I've got you started here. I'd like you to try to finish it. I will tell you, when I did it, I got about just over 12 meters per second when that thing finally hits the ground. So I'd like you to try to finish this. If you have questions on it, how I got 12, email me, I'll let you know. In addition, as all these ideas are in the homework stuff, and I looked pretty carefully to make sure to keep us on track, I see no reason why you can't get through homework question number 29 in the homework, even pass it actually. If you have questions on any individual homework question, email me. I'll help you through it. I'll give you a couple of hints. But we need to keep moving forward. In a 2-trimester class, we can't afford a 5 or 6 day span like we've had, where we just don't get a chance to meet. So again, if you have questions, email me. I will help you as much as I possibly can. I will see you tomorrow.